priority queues, right? General concept of priority queue is that, as you can see from the name, it's just ordered based on priority. So the one at top will be highest or whatever is based on high or low. And then this chunk of stuff will have a little lesser than that. This chunk will have a little lesser, and it just goes like that. At the top will be of highest priority. That's the main thing here. So what are the operations here? It's insert, delete, and find min or find max. So the data structure we're using here is going to be heaps. So coming to heaps, right? This is a complete binary tree, right? So it's gonna look something like this. It will be inserting like this and it'll be going. Important thing here is something called the heap property. This is what differentiates it from just being a binary tree, right? So for a min heap, the property goes like this. The parent will be lesser than or equal to the value of the child, right? So always it's gonna be like, let's take an example right here. 5, then something less than 5, 4, something less than 5 is 1. Let's take 2. Then let's take 3, 1, 0, anything like that, right? So oh shit, sorry, wrong way around. I think I took opposite way. Let's take 5, 15, 10, 20, 25, 11. Okay, this is a min heap. The element at the root is going to be your minimum, right? Same thing like this. When you do it the opposite way around, it's going to be max heap. This is when parent is greater than or equal to child. Example, what did I say before? 5, 4, 1, 3, 2, 0. Yeah, this is example of max heap. Key point here is the root is always the maximum or the minimum according to which type of heap you are taken, right? So that is generally what is heap. So to maintain this kind of order, right, there is a function. This is called Heapify. This is a function to maintain heap property. This is of you have two Heapify functions. First is let's take Heapify up. So what happens is it makes sure it makes sure that the heap property is satisfied going up. So let's take Heapify up of this particular node, right? What it's gonna do is you're going to take this node, take its parent, and check if heap property is satisfied or not. For this example, I am going to take A less than B less than C less than D, and I'm taking for a min heap, okay? Here on, I'm just going to be taking min heap. Just the equality, if you shift it the other way around while checking, it's going to become a max heap. I'm not going to repeat the same thing. So you're going to check. Here it turns out that the A is less than B, right? Heap property is not satisfied. So what it's going to do is it's going to swap these two. So what it's going to look like? A will come here, B will come here, C and D remain as it is, right? And then further, whatever B was connected to up and all is gonna remain the same, but it's gonna be connected here. So what you have to do is check for it, check heap property again for these two. You are gonna keep checking and keep swapping whenever it applies, right? So when are you going to stop? If property is satisfied or root is reached. These are the only two stopping conditions for Heapify up. Okay. Now, same, we did this going up, right? What if we did this going down? This is Heapify down. Let's consider C. So, Heapify down, you are supposed to check this node along with this child, same node along with this child, check for both. If heap property is not satisfied, you have to swap with the minimum of these two nodes, right? So here I said this condition, right? I put it here first. So I'm gonna swap C and B together. So after swap, it's gonna look something like this. A is here, C and B I'm swapping. So B will come here, C is here, D is here, and further children will still be here. Again, same way as we did for Heapify up, you are going to keep checking here also, and then swap again if applies, till you reach a leaf node or property satisfied, right? So that is how this thing goes. So we took heap as a complete binary tree, right? So the maximum possible number of swaps it can make is log n, right? Because complete binary tree, height will be log n maximum. Let's just take a look at the algorithms. This is what we just went through. Heapify up, you compute the parent, check for heap property. If it is not satisfied, swap. If it is satisfied, then that's it. Job is done. Heapify down, you calculate the children. If you see which of them is smaller, right? And then you swap with it accordingly. Break if property satisfied. So now we're going to use arrays to represent this, right? You know how to represent a binary tree with arrays. You just keep populating it like this. So insertion concept is this. So how do you insert for normally for a binary tree? How do you insert? You just add it to the end, right? And then one thing you need to do is heapify up for it now. So when you Let's take it with an example actually. I'm going to insert all these elements here. First, I will insert 50. So now there will just be a node for 50 here. In your array, how many elements are here? 1, 2, 3, 4, 5, 6. I'm gonna make an array of size 6. Right. So index. So here I'm going to put 50. So then next insert, I'm going to take 30. Level order insertion. I will put 30 here. Min heap. So I'm going to check heap property here. It is not satisfied, so I'm going to swap. So after swapping, it's going to become 30 here and 50 here. So array will now look something like this. 30 here, 50 here. Right. I'm going to insert 40. 30, 50. Again here 40. Um, you can see here min heap property is satisfied, so we are not doing heapify up here. Right. So here it's just gonna append 40 here. Insert 10, 30, 50, 40, and then here is 10. Now check heap property here. It is not satisfied. So now it's going to swap here. 10 will come up here. 50 is going to come up here. And then 30 is still here, right? Check here again. Again, heap property is not satisfied. So it's going to be 10 here, 30 here, 50 here, and then there's a 40. We've reached the root. So Heapify is fully done. What all did we change? So here is 10, 30, 40, 50. And then you can just keep going on like that. Same thing only, just stop where the heap property is satisfied or you reach the root. So algorithm is just what I described just now. Just append it to the end and then you're just increasing the size here, nothing bigger than that. And then you apply Heapify. So here let's talk about best case and worst cases, right? So for Heapify up, best case is when you're doing Heapify up for the root itself, it'll be off one, best case. Worst case is going to be O log n for leaf. Heapify down, is going to be the opposite of this. Best case is going to be it being the leaf of one, best case. Worst case is going to be root, you have to travel all the way down, of log n. Okay, right. Then insertion, best case is your element when you append it, it's in correct position itself. you don't need to apply Heapify. This is best case O of 1. Worst case is you just appended an element that is supposed to go till root, right? Worst case O of log n. Now let's move on to deletion. Now we're gonna do deletion given its position in array. So what you're going to do is uh, let's take this example here. What if you want to delete 10 here? What you will do is you're going to this is the last node here, right? You're going to first swap. So it's gonna look something like 50, 30, 40, and 10. And now you're going to delete this. And this node is probably it's gonna be in an unsorted position. So you have to apply Heapify down here. So here one swap will happen. So it's gonna look like 30, 50, 40, and yes, that's it. So here total cost here is gonna be O of log n. Best case is if the element you swapped with is in the correct position, this is possible. So it's gonna be O of 1. Worst case is if you delete the root, then it's going to go through Heapify all over again. So it's gonna take O log n. And then you're not using any extra space. So that's deletion. Find min. For min heap, minimum is at the root, right? This you can just take directly as array of 0. And that's job done. Time O of 1. No extra space. So that is deletion and finding minimum. So let's look at a few things. So one insertion is going to take you log n time. N insertions is going to take you n log n time. So if you want to construct a heap, then your complexity is going to be O n log n time. So heap construction is this. Now let's look at the other side. One deletion at root will return minimum here is going to take log n. N deletions, each time returning a minimum. Let me just mention root here. Is going to take n log n. So you delete once, you get the first min. After you delete it, second min will take its place. And it's going to go on. So as you keep deleting, you're going to get it in a sorted order. So this is basically what heap sort uses, right? You're supposed to construct the heap and then pop from it, and then keep deleting the root from it, and you're gonna end up with a sorted array. So construction is gonna take O of n log n. Deletion is gonna take O n log n. Overall cost is gonna be O n log n, right? And this is heap sort. It's a really good comparison and swapping algorithm. So when do you use heaps? Let's look at some applications. First is for heap sort. And when there is frequent use of minimum or maximum. If it is just like finding minimum or maximum once, you can directly use linear search. That should do your job, because that will take O of n time. It's going to take O log n every time, right? So if it is frequent, you use this. So yeah, so here we've covered um, till now. We only saw for frequent minimum and maximum. We are gonna use heaps and priority queue, but best case for general search is still best O of log n base 2 from AVL trees. That is the best we have till now. Let's look at some other things.
So B trees are n-way trees. They can have multiple children, like binary trees, which are restricted to two children. So they have some properties. Firstly, uh, if the order of a B tree is m, it can have up to m children. And it can have a maximum of m minus 1 children per node. Oh, sorry, elements per node. A node maximum. And it also enforces a minimum number, which should be m minus 1 by 2 float. So the maximum number of elements divided by 2 float is the minimum number of elements per node. Now, every node follows this except root node, because obviously when you start, the root node will have 0 and then it will have 1 and so on, right? So the minimum is not enforced there. For the minimum, the root node is not considered. For the maximum, it is considered. And B trees, all the leaves are at the same level. That is, they are balanced trees. Now, how do they achieve this? So, let's consider an example. Let's say we allow a maximum of 5 nodes, 5 elements in a node, and this is our root node. Let's say we insert 1, let's say we insert 3, and then we want to insert 1. Another property is that the elements are sorted in nodes. So we start with 3. If you want to insert 1, 1 would become the first element, 3 the second, and then let's say we want to insert 10, and then 7, and then 8. Now we have reached the maximum. If we wanted to insert one more, say 5, what would happen is we would split. How the splitting occurs is we take the left half and the right half and then create 2 nodes from those. And the minimum number of elements here is 5 by 2 float, 5 by 2 float, which is 2. So how we split this is we would keep 7 in the root node and create 2 new nodes for the left and the right. So we have 1, 3, 5, and then 8, 10, right? Let's say we insert 2 and 4 and say 9, 11, 12. Actually, let's keep this like this. And let's say we want to insert 6. Now what would happen is we create a split again, but remember that we want all the leaves to be at the same level. So we don't uh, create a new node for the central or the middle element, right? So we don't create a new node for 4. What we do is we take 4 and put it in the root node or the parent node. So it becomes 4, 7, and here we get a singular new node with 5 and 6. Let's say 3, 4 is there, 5. Now a pattern you can see is everything lesser than this node will be on the leftmost node. Between these two values is present here, and between this after 7 it's present here. So these function very similarly to binary search trees, but instead of a simple lesser than and greater than comparison, we have multiple values or multiple ranges of values we can split into. So instead of splitting by 2 each time, we can split by up to m ways. The order of the tree is the maximum amount of we can split by. Now deletion. For deletion, uh, normally if you want to delete an element, you just delete it. But what if the minimum number of nodes, minimum number of elements is already the number of elements present in a given node? Once you delete it, the minimum property disappears. So then we do the reverse. Then we have two options. One is to get from neighbors, or siblings rather. So let's say we are going to delete 6, right? So if we delete 6, we only have a singular element here, and the minimum number of elements per node is 2. So what do? We can either take from this node or this node. Uh, we are going to ignore this node for now because that also has a minimum. So we can take from here. So when you're taking from the right node, you want to take the minimum. When you're taking from the left node, you want to take the maximum. So that's because the maximum of the left node will be lesser than the minimum here, and the minimum of the right node will be greater than the maximum here, right? Now you can't just take 8 and put it here because then this range is not valid. 8 is not between 4 and 7. So what we do instead is we promote 8 to the root node and put 7 here. Say we had 3 here as well. So if I had not deleted 3, we could have taken from here as well. In that case, what would happen is we'd have 5 here. 3 would get promoted to the root node and you would get 4 here. So this process is called merging. Okay. Is it merging? Sorry, this is called redistribution. The second thing we are going to look at is called merging. This is called redistribution because you're redistributing elements from sibling nodes, right? And the second one is merging, which is what the name suggests merging two nodes together, two siblings. So let's say now we delete 8 as well. If we want to delete 4 now, what would happen? We can't redistribute anything because all of the nodes have the minimum number of elements. So we will have to merge two nodes together. So for merging, what you do is you take the left node or left and right nodes that you're going to merge, which can be either node here. Let's take 1, 2, and 5 here, and you merge them into a singular node and include the separator from the root. So these two nodes are separated by 3. You include that here. You remove this node completely and you merge it here. If we were to merge it with another node, we could. Uh, in that case, you would get 5, 7, 9, 10. 7 would be gone from the root, and the BTD properties are satisfied. Remember, the root node can have less than the minimum number of elements. That's the only exception. Now, both the merging process and the splitting process can recurse. What that means is, as you split nodes, you might be forced to split again. So let's say the root was full. Let's say we had like 8, 10, 12, 14, and 17 in the root. Uh, and we had 1, 2, 3, 4, 5, 8 and 10 we have. Okay, you wouldn't get that. Uh, what is there? 18, 23, 27. Let's say we had 9, 11 here. 13, 15, 16. Um, okay, let's move these. Oh, um, okay, let's see. And let's say we had this here beyond 27. And let's say this node was full. So 28, 29, 30, 31, 32. And say we inserted 33 there. Then what would happen is you would try to promote one more entry to the root node, but that would not be possible. At which point the root node itself would split. So you would be promoting 31 to the root node. So you would get 31 here, which is more than what it can contain. So you would split like this, and 23 would become the new root. So you'll get 23 here. Then you'll get another, with 27 and 30. And this node would contain these things, right? So you'll get this and this, and this node would now connect it to be bit. This node is also being split into 30 got promoted. 31, 32, 33 will be a new node. So between 27 and 30, you get 28, 29, and 31, 32, 33. 31, 32, 33. So the split algorithm recurses like this, and similarly, the merging algorithm can also recurse. You might have to continually merge nodes upwards when you delete an element. You might have to continually split nodes when you insert an element, right? So you can see that by splitting upwards instead of downwards, all the leaves are at the same level. So these leaves are at the depth of 2, so are these leaves. And this will always be true no matter what. So that's how you insert and delete from a B tree. Is there anything else? Yeah, I don't think there's anything I'm forgetting. Searching, as I already mentioned, it's just like a binary search tree, except that you have the added benefit of splitting multiple ways instead of a single way. So these are for deletion, and splitting is for insertion. Insertion overflow, you split. Deletion underflow, you try to redistribute. If you can't redistribute, you merge. Uh, Redistribution is non-recursive. You only have to do it once. Whereas splitting and merging are recursive in nature. You might have to continually do it, depending on how full or empty the nodes are. Okay, uh, so that's it for decrease. Next up, we have infix to postfix conversion and postfix expression evaluation.
One
So
moment.
let's do convert.
Did you cover the complexity?
No,
Yeah,
do they
just
need it?
mention complexity for searching in B tree is log n base n.
Uh, insertion and deletion are also log and base m in the worst case when you recurse upwards and all the way until the root. Redistribution is constant time. but deletion can trigger merging, so deletion complexity overall will be considered log n base n. Insertion is just plain log n base n, based on the worst case. Okay. Um, yeah. Infix the postfix. Let's So we have operator precedence and associativity. So I'm pretty sure you guys are familiar with this. Let's take an example equation and explain the process with that. To, yeah, let's take a minus b plus c time times d all over e. So when you're converting from infix to postfix, you're going to keep track of two things. One is an operator stack where you put operators into and pop operators out of. Let's say this represents our stack. And then you just have the output, which is the postfix expression. So with all the operands, the variables or numbers in the equation, what you do is you just add them to the output as is. So operand A, add it. Operator, you add it to the stack, and when you encounter a parentheses, you add it to the stack and add all the operators to the stack as normal. And when you encounter the closing parentheses, you keep popping off the stack until you encounter the corresponding opening parentheses. So that you make sure to evaluate this entire expression within the parentheses, right? So next, this parentheses essentially makes this an a new substack, so to speak. So we don't care about this subtraction right now. We have a plus, and then you have a multiplication. Now, when you already have an operator in the stack and you adding a new operator, if the operator has the same precedence or higher, so if this has same precedence or higher than multiplication, you pop it off the stack and add it to output. Addition does not have a higher precedence, so we just add multiplication to the stack. And then you have the closing parentheses, at which point you pop from the stack and add it to the output. So first would have been multiplication. Oh, sorry. B and C are added to the expression here. B, C, and then and D, 2 before the closing parentheses we encountered. And then multiplication and then addition. And now division is added to the stack and then E, and you reach the end of the expression, so you pop everything from the stack. So it's division and then subtraction. Now let's look at the same equation without the parentheses, right? So what would happen then? That's fine. So C times D divided by E, right? So same deal as before, add A to the thing, minus goes here, B and plus. Now addition and subtraction have the exact same precedence, right? So what you do is you pop uh, the minus and then you add addition to the stack. Then you have C, multiplication has higher precedence than addition, so you just let it be. And then D, now division and multiplication have the exact same precedence. So you add division to the stack after popping multiplication, and then E and end of equation, you pop everything, slash, and then, right? Now for dealing with the exponentiation operator, for exponentiation, the associativity changes from uh, left associative to right associative. To deal with that during conversion, what you do is when you encounter uh, an exponent at the top of stack, don't pop at equal precedence. So if you have an exponent and at the top of the stack and you get another exponent, do not pop it, just add it to the stack. Whereas with the other operators, you pop it even if it has an equal precedence. For exponent, to deal with associativity, you do not pop it from the top of the stack. And that takes care of the right and left associativity of operators. So now we have postfix expressions. How about building, evaluating these expressions? We do that by building expression trees. Now this also uses a stack. Or what you do is you go over the expression. Let's take this one. Yeah, there we go. And we, let's say we have a stack here. Should be enough. As you encounter new operands, you create new leaf nodes. Operands will always be the leaves. The root node and the internal nodes are going to be the operators. So first two operands we created leaf nodes, and when you encounter an operator minus sign here, you pop twice from the stack, uh, and then create a new internal node with the operator and their left and right child being the two nodes that you popped from the stack. So enter a node. The left side, the right side. Okay, and then you repeat the process. We have C and D, so you add leaf nodes to the stack, and then operator. So you pop twice. So after you pop, these are the two recently added nodes. So you pop C and D from the stack and multiply them together and add it back to the stack. So multiplication. C, D. And then you have E. And then you pop twice from the stack. You get division. E here, multiplication of C and D. And again, you have an addition. So you create a addition goes at the root. So our equation would be A minus B plus the division of this. So C times D, then divided by E. So that's postfix expression evaluation using expression trees.